we already know that digital circuits are constructed using integrated circuits. And what are these integrated circuits, or what we call ICs fondly? They are small semiconductor crystals or chips, typically silicon crystals or chips, and they contain electronic components that constitute digital gates. They are typically mounted on a plastic or a ceramic container, um, so that they are resistant to heat and temperature changes. And then the connections are welded to external pins. So the ICs that you have been seeing so far, you all know that there are external pins which are welded, right? So the actual connections are then welded to the external pins. Now, an example of this is a 14-pin IC. For example, 7400 that you have been using in digital logic. There can be a larger IC like 64-pin or even more. A typical size of a 14-pin IC, the one that you've been playing around with, is around 20 mm by 8 mm by 3 mm. And there are various types of packing that ICs use. For example, dual inline packaging, DIP. This we have discussed in class earlier. This is how your typical DIP packaging looks like. So there is literally a dual line of connections, like a symmetric structure of connections, right? So typically, like this is a 14-pin IC. The other type of packaging is called metal can or transistor pack. We'll see an example of that as well. And then the third type is flat pack. So note that these are not the only 3 types of packaging. There are multiple versions of these kind of packaging for different applications. But broadly speaking, at a very basic level, we can think that these are the 3 broad types of packaging of ICs that you will find: dual inline packaging, metal can, and flat pack. So here are some examples of ICs. So you can see that this, what you see, this one, and this one, these are called metal pack or transistor pack. Like there is a like a button sort of structure, a can sort of structure, and then there will be pins coming out. Okay, these are what are called flat packs. Okay, now the type in which they will be mounted, that also can differentiate the type of ICs. Like how they will be mounted. This will be mounted on a surface, right? But this will be going into the holes, like vertical holes, like of your breadboard. Okay, so these are some types of ICs. You are welcome to explore and find out what are these different types of packaging. Okay. Now, question: is Arduino Uno an IC? So the answer is no. Arduino is a microcontroller board. Okay, it has its own IDE, that means integrated development and environment, like its own programming language and everything. And there are multiple ICs present on an Arduino board. So the main microcontroller that you use, that is called Atmega 328. This one, this is that IC. This is one of these ICs. Then it also has a oscillator, which is also on an IC. Okay, it also has a voltage regulator. This is also an IC. Okay, there is another small microcontroller IC to USB control. This is also an IC. You can see that this is like a flat pack, and this is DIP packaging, right? So an Arduino Uno is not an IC. It is a microcontroller board containing multiple ICs. Okay. Now, coming to levels of integration, I remember somebody had asked this in class earlier. So there are, by integration, we mean how many components or how many gates can we compact on a particular chip on one particular platform, right? So the very basic one is called small scale integration, SSI. It has less than 10 components. Next is medium scale integration, when on a chip you have about, say, 100 components, less than 100 components, but more than 10. Okay. Large scale integration, when you have more than 100 components, LSI. And very large scale integration, or VLSI, is when you have more than 1,000 components on one chip. Okay, so this is a very easy question. Can you give me an example of SSI One such type of SSI family chips that you know already?
7 4.
7400,
Full reader.
right? Because
Fans.
these are all like quad NAND, quad NOR, right? There are like less than 10 components, less than 10 gates on one IC. When we talk about medium scale integration, here you will have ICs that contain decoders, adders, multiplexers, like single ICs which contain this entire circuit. So you know that they will need more than 10 gates, of course. Then LSI में आता है processor chips or memory chips, RAM, etc. Then very large scale integration, VLSI में you will find like a proper entire microcomputer built into a chip that will come under VLSI integration. Next is digital logic families. Now, what is the meaning of digital logic family? Now, digital ICs, they are not just defined in terms of the complexity of what logic operations they can do. Okay. Every digital logic family uses a specific circuit technology, like the basic circuit that they will use to create any gate, the basic underlying electronic circuit. So that specific circuit technology, which is used to manufacture or create an IC, is called a logic family. Every logic family will have its own basic electronic component, one of which you have already studied, okay, upon which more complicated circuits will be built. You know, more logic gates or more components, more layers would be built. So the basic circuit in every technology, this we already know, are one is inverter. This is what we studied earlier when we were studying BJT as well, because inverter is the NOT gate is the very, very basic element of digital logic. And then the universal gates, NAND and NOR. So every basic circuit in each technology will have NAND, NOR, and inverter. Now, the name of that logic family essentially comes from the basic electronic component which will be used to construct the basic circuit. Like what will you use to construct NAND or NOR or inverter in each of these families? That is how the name comes from. So I again don't want to go into the details of each family, but broadly you should know what these families mean. I'm not going into the circuit of each technology, each family, that you can find out for yourself, but for the scope of this course, that may not be needed. Okay? So one basic logic family is called transistor logic, TTL. Yahan pe you can clearly see, right, what must have been the basic electronic circuit, right? This is a BJT based logic. Next is called emitter coupled logic, ECL. Here, this is also a type of transistor, but there are multiple emitters coupled to the base. Next is metal oxide semiconductor. So the basic that we had studied when we started talking about BJTs, right, was why is BJT called BJT, bipolar junction transistor? Because it uses both types of polarities of carriers, right, for the flow of current. This is opposed to what? This is opposed to metal oxide semiconductor or field effect transistor. BJT is bipolar junction transistor, but FET is also a type of transistor, okay, but field effect transistor. This you will study later. It's not a part of this course, but today's technology is often dependent on, like the ICs that you see today are mostly MOSFET based. So FET is this field effect transistor and MOS stands for metal oxide semiconductor. MOS, metal oxide semiconductor. And the last part is complementary metal oxide semiconductor. This is also, you can say, an extended form of MOS. Okay? Now, there were earlier some more digital logic families, like which are now obsolete. They are not used anymore, but they were like diode transistor logic, diode resistor logic, a few like these. These are obsolete now because they were very slow and they would consume a lot of power. They are not used anymore, but these four families are still used depending on the application. Now, if you wanted a simple and standard kind of operation where you're just doing experiments, right? There, TTL logic will be good. It is very simple, it is very standard. And an example of TTL logic family is the 7400 series that we have been using for our lab experiments. However, if you wanted a very high speed operation, you would not go for TTL. You would then go for emitter coupled logic, ECL. Okay, ECL is useful for high speed applications because it can operate in nanoseconds. If you were looking for a high component density means in a small area, how much of component you can actually stuff, how dense you can make it in terms of components. If you were looking for a high component density, you would go for MOS logic family. And if you were looking for absolutely low power consumption and high component density along with it, you would go for CMOS. A lot of today's ICs, which you typically see in microprocessors or controllers or your computers, are based on CMOS families because they have to do a lot of operation, but they should not consume too much power, right? So this is an important slide. So I would like you to go through it one more time. TTL is simple. ECL is what you would use for high-speed operations. MOS is what you would use for high component density. And CMOS is what you would use if you were looking for low power consumption. Now, characteristics of digital logic families. This is also something like you should be familiar with what are some specifications that define a logic family. These will be different for different logic families, but you should be familiar with at least some basic names of such specification. So one such thing is called fan out. Note that these are characteristics, okay? Like these are, जैसे op-amp पढ़ते time हमने देखा ना, op-amp का एक slew rate होता है, एक input resistance होता है, CMRR होता है, gain होता है. Those are what? Those are characteristics of that particular op-amp. So like this, these are characteristics or specifications of a digital logic family. So first such characteristic is called fan out. Fan out essentially says how many number of standard loads that you can actually connect to the output of the gate, and they will be driven. Output of a gate is having a particular fixed voltage, right? And it would have a fixed amount of current flowing out of that terminal. So how many loads can you connect so that the output is still able to drive those output? You cannot connect indefinite number of components at the output of any terminal, right? You cannot connect indefinite number of loads. So every logic family can handle some particular number of loads that you can connect. For example, 10 loads. 10 can be one family's fan out. So the specific number of standard loads that the output of a typical gate can drive without impairing normal operations, meaning without getting overloaded, without being able to supply sufficient amount of current to every load, without the actual operation of the gate being hampered. Like it was supposed to do inversion, but it's not able to do inversion anymore because there's too much load on the output, something like that. Next is power dissipation. This you understand, obviously, how much of power will be consumed by the gate, and that should be available from the power supply. So of course, in an ideal gate, we would want that the power dissipation is minimum, as low as possible. Next is propagation delay. Propagation delay is the average transition delay for a signal to propagate from input terminal to output terminal. Like how much of time will it take for a signal to enter the input terminal, get processed inside the circuit, and then finally result in an output. This interval, this is what is called a propagation delay. And we understand that ये propagation delay जितना ज़्यादा होगा, speed of operation उतनी कम होगी, right? So that is what it says. Operation speed is inversely proportional to propagation delay. In a gate or in a logic family that we want to use, we want that propagation delay should be as low as possible. So if I wanted a very high speed operation, I would use which logic family? Emitter coupled logic, ECL. And I know that there the transition delay is like in nanoseconds. Next is noise margin. This is also a very important factor. Noise margin is the minimum external noise voltage that causes an undesirable change in the circuit. What do we understand by this? So let us look at it again. It is the ability of the gate to tolerate fluctuations in voltage levels. What does that mean? Think of the input characteristic. This is the input side of a gate. Okay, we know that these are logic gates, right? That means depending on a certain voltage level, it has to, every logic gate has to define कि इस वोल्टेज से नीचे यदि वैल्यू है तो हम इसको लेवल 0 मानेंगे. Let anything between in this interval, let it be considered to be logic level 0. Okay, and anything above some threshold, let everything in this region be considered as level 1, right? You cannot have every time, you already know, like see, think of when you studied BJTs, right? उस टाइम आपने क्या पढ़ा? आपने पढ़ा कि सैचुरेशन मोड में VCE की वैल्यू लगभग 0.2 वोल्ट होती है या इससे भी कम होती है. तो हमने इसे ओवरऑल क्या बोल दिया? यस, दिस इज अ लो लेवल. It was not exactly equal to 0, right? This is how in practical application there cannot be like just one hard threshold which you can use and say कि okay, yes, this ये voltage है तो high है, ये voltage है तो low है. No, you have to define a range. Okay, so what this basically means is कि इस range में कोई भी values हुई, it will assign it a logic value 0. इस range में कुछ भी हुआ तो it is going to assign logic level 1. ये जो बीच का एरिया है, this area, this is the area which is undefined, it is indeterminate. Okay, अगर आपका वोल्टेज इस रेंज में है, indeterminate, अगर आपका वोल्टेज इस लेवल पे है, the gate doesn't know whether to assign it level 0 or level 1 or what to do. Okay, so this level should be avoided at all costs. Why does it have this kind of a margin given? So that even if there is some noise, you can still accommodate. Like originally the signal value was supposed to be 4 volt and this was supposed to be high, but because of noise the effective value that you are getting is some 3 volt. Okay, now what is the meaning of noise margin? What noise margin essentially means is that if I was looking at output characteristics, this is the output characteristics, okay, towards the left, and this is the input characteristics. In input characteristics, the range of logic high and logic low is much higher, usually kept higher, and in the output, the range of logic high and logic low will be kept narrower. It is this difference between the two thresholds is what is called noise margin. This is what is called noise margin. कहने का मतलब क्या है कि सपोज आपका कोई गेट है जो आउटपुट में अगर 4.5 वोल्ट आता तभी वो उसको लॉजिक लेवल 1 मानता है, हाई मानता है. ठीक है, बट यही सेम गेट इनपुट में 3 वोल्ट को भी हाई मान लेता है. क्यों? क्योंकि इनपुट will be more prone to noise. So in the input side, it is allowing a higher noise margin, you can say. It is allowing a higher noise margin to accommodate for the noise. The same gate on the output considers 4.5 only as high, but the same gate on input can consider 3 volt to be high. Okay, that means 1.5 volt, right? The difference between the two threshold, output का threshold क्या था? Suppose मान लीजिए 4.5 के ऊपर को ये 1 मानता है, तो 4.5 माइनस इनपुट के लिए हाई थ्रेशोल्ड क्या है? 3. सो नॉइज मार्जिन वुड बी 1.5. in such a case. The same will be true for lower side also. This is what is meant by noise margin. Okay, so if, in other words, if you look at the term noise margin, it is essentially just the higher the noise margin, the greater is the difference between what is considered a valid high and a valid low without going into undefined region. मतलब undefined indeterminate region में गए बिना that much of noise can still be handled by your circuit, by your logic gate. That is what is called noise margin. Okay. Next is about ICs. So this I already discussed in class once. There are IC हमेशा digital IC नहीं होती. IC can be analog IC depending on what operation it does, or it can be digital IC. Analog IC का एक example है LM741, which is an op-amp which you have used. Another example is LM723. This is a voltage regulator. This is 723. It has a Zener voltage, Zener diode, of course, within it, but it has a lot of other things also. Okay, so analog ICs are one such case. Digital ICs are all these 700s that you are seeing, and there may be multiple other ICs like BCD to 7-segment converter. I think is 7447. Lots of such ICs are there. Okay, you should be able to differentiate between analog and digital ICs based on what you're already familiar with. Next is the name of an IC. Like IC में कई बार बहुत सारी चीजें लिखी हुई होती हैं, right? What is the meaning of those things? So, for example, you may see ऐसा कुछ लिखा हुआ IC के ऊपर MU-A741TC, या ऐसे लिखा हुआ MC34001P 0 to 70 degrees, या MU-A723F8016. What is all this? What does this mean? Now, company. Or LM101AF, right? So essentially, these are meant to represent what are the functional and electrical characteristics of the device. They also show what is the packaging type. They also show what is the temperature range for application of this IC. Is it military grade? Is it industrial grade? Is it for commercial applications? Okay, but there is no consistent format. So like there is no one single format that all ICs follow. So you always have to refer to the data sheet of the IC. Okay. Typically, the first two letters are representing the manufacturer. So MU-A stands for Fairchild. MC is Motorola. LM is National Semiconductor. I think this was later acquired by something else. So letters may have changed. So suppose, let's take an example, MU-A741TC. So you know that MU-A means it is manufactured by Fairchild. 741 is an op-amp. 741 is not the only number that is identified as an op-amp. हम देखेंगे मोटरोला में कोई और नंबर को op-amp से आइडेंटिफाई करते हैं. T is standing for mini DIP packaging, dual inline packaging, but mini 8 pin है केवल इसमें, right? And C stands for commercial temperature range, yani 0 to 70 degrees. This is the temperature range for operation of this device. Similarly, MC34001P 0 to 70. MC is coming from Motorola. 34001 is again an op-amp. P stands for DIP, but plastic. And 0 to 70 degrees dikh raha hai that it's a commercial temperature range. This is the name, MU-A723PC. So MU-A आपको पता है comes from Fairchild. 723 I just told you in an earlier slide.
Voltage regulator.
Voltage regulator. P will be some packaging, and C is temperature range, right? F is again coming from Fairchild. Now this 8016, this first two digits are year of manufacturing. Like this chip was manufactured in 1980 and on the 16th week of 1980. So last two digits are week number. Okay, so like this, there can be very different ways of what is the information available that you can read on an IC. Like I said, there is no one consistent format. You always have to refer to the data sheet, but you should have some idea of what is that information on the IC.